Hi everyone, and welcome to our lecture video on section 1.4, differentiation using limits of difference quotients. So the two objectives here, we're going to learn how to find what are called derivatives and values of derivatives, and we're also going to work on finding equations of tangent lines. I want to start at the bottom of page 1 with a really important definition. It talks about finding the slope of the tangent line at a particular point. Now, as a reminder, in our previous section 1.3, we were looking at any kind of function represented by this curve, and we would pick out two particular points and find the slope of the secant line. And that secant line connected our 2 points. That slope for the secant line also represented the average rate of change for that function. What we're finding now is the slope of a tangent line at one particular point, x, comma, f of x. So notice here on the illustration, you've got this one point P that has a tangent line, and we're wanting to find the slope of that tangent line. Now this slope, m, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That hopefully looks familiar. That fraction is just the difference quotient that we learned in section 1.3. The only difference here is that we're now taking the limit of that difference quotient as h approaches 0. And when we take the limit as h approaches 0, the slope of that secant line is getting closer and closer and closer to the slope of that tangent line. And this limit is also the instantaneous rate of change of f of x at x. In other words, instead of using 2 points and finding an average rate of change, by taking the limit as h goes to 0, we're finding the exact slope of the function at that one particular point. So here's what's crucial to understand. If the original function is represented by this curve, and I'm focusing on this one point P, the slope of the tangent line and the slope of the function are exactly the same at that specific point. So notice when you look at the original curved function, its slope is going to be different depending on where exactly this point is located. So we're going to use this difference quotient, take the limit as h goes to 0, and that's giving us the slope of the function at that point. Also, it gives you the slope of that tangent line. So the next definition just kind of redefines or gives this process a label. For a function, y equals f of x, its derivative at a particular x value is called the function f prime. When you see that little stress mark on the f function, we call that f prime, and it represents the derivative of the original function at a particular point. And this derivative, f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that limit exists. If f prime of x does exist, then we say that f is differentiable at that x value. And again, what you're looking for when you've got this original function represented by the curve, pick out some particular point. If I want the slope of the function at that point, it's the same as the slope of this tangent line at that point, I'm going to find that by using this so-called derivative of the original function. Let's go ahead and look at our first example. So down at the bottom of page 2, they give us this function f of x equals x squared. They ask us to find f prime of x, that's its derivative, and then find f prime at -3 and f prime at 4. This process starts by finding the difference quotient. And this is something we already know how to do. We learned how to find the difference quotient back in section 1.3. Remember, this is going to be f of x plus h minus f of x all over h. So in this example, our function is x squared. So I take the x plus h, I plug it in for x. This becomes x plus h squared minus the original function itself, which in this case is just x squared, and it's all divided by h. Now, hopefully by now we've squared out this binomial a couple of times. We did it at least twice back in section 1.3, so I'm going to kind of cut to the chase on that one and write out the results as x squared plus 2xh plus h squared, and then minus the x squared at the end. This is all divided by h, and now we're going to see a lot of nice canceling taking place. So we've got the x squared front and back, those cancel. The next step, we're going to reduce every remaining term by a factor of h. So in this case, our final answer for the difference quotient is going to be a 2x plus h. Notice 1, 2, 3 terms that were remaining, I reduced all of them by a factor of h. So that's our difference quotient. Now, what's new in section 1.4? We now want to take that difference quotient and we want to find the derivative of the original function. So now I'm finding f prime of x. This is going to equal the limit as h approaches 0 of that difference quotient. So in this case, 2x plus h, and you've got a really nice simple limit to evaluate here. If you take the limit of 2x plus h as h approaches 0, you're left with just 2x. So 2x is the derivative for our original function. And what I want you to think about, this derivative is basically like a formula for finding slope at any particular x value. So what you're seeing here with the follow-up questions, now they ask us to find f prime of negative 3. Well, that's going to be 2 times negative 3, which is negative 6. That negative 6 is the slope of this function at this x value. Now, before I do the last part, I really want to make sure we understand that concept. The original function x squared is just a parabola. You know the vertex here is located at 0, 0. So if you look at the x value, negative 3, here's 0, 0. Negative 3 is going to be somewhere over here to the left of that vertex. What we just found with this negative 6, that's the slope of the function at that location. Remember, derivative finds slope. So next, they ask us to evaluate f prime of 4. So f prime of 4, that's going to equal 2 times 4, equaling positive 8 for the final answer. And again, what that represents, this is the slope of the function at that x value. And we're finding that that slope is positive 8. Okay, so I guess the takeaway so far, and what I would really want you to focus on and really try to remember, is anytime you see a derivative, you know you're finding slope. And it doesn't really matter if they ask you to find the slope of the function or the slope of the tangent line. Those two things will always be the same at that particular x value. All right, we're going to go a little bit further at this point. So let's turn our guided notes to the top of page 3. In our next example, they give us the function f of x equals x cubed. They want us to find the derivative and then evaluate that derivative at negative 1 and at 1.5. Now again, this process starts by finding the difference quotient. So I'm actually going to come up here to the top where I have a little bit of room, and I'm going to start. So this is my difference quotient. Now again, I think we had this particular difference quotient back in section 1.3, so it hopefully seems pretty familiar to us. I am going to go through the steps just to make sure. But remember, this difference quotient starts by taking the x plus h, plugging it into the function. So that's going to give you x plus h cubed minus the original function itself. And then I'm dividing that difference by h. Okay, so let's go ahead and remember that's x plus h times x plus h times x plus h. So I'm going to have one binomial, x plus h, and I'm going to FOIL the other two together. When I FOIL those other two together, I'm getting x squared plus 2xh plus h squared. And then I've still got that minus x cubed. I divide that whole thing by h. Next, let's multiply our binomial with the trinomial. That starts by distributing the x. When you distribute your x, you're going to have x squared. X cubed rather. Let me correct that. You've got x cubed here, and then plus 2 x squared h plus xh squared. Next, I'll distribute h to all three of these terms as well. So that's going to be an x squared h plus a 2 xh squared, and then finally an h cubed. Don't forget you've still got the minus x cubed at the end, and this whole thing is still over h. And now the fun part, right? Now the canceling. So the x cubed at the front, x cubed at the back, those cancel. I've got a couple of like terms in that numerator that I'm going to go ahead and combine. 2x squared h here, 1x squared h here, that's 3x squared h total. So let me jot that down. I've got a 1x h squared, 2x h squared, that's 3x h squared total. So 3xh squared, and then don't forget that h cubed at the end. Now I'm ready to reduce my fraction. Remember, as long as you do this consistently, every single term in this fraction is divisible by h. So this is going to reduce and become 3x squared plus 3xh plus h squared at the end. And that entire expression is our simplified difference quotient. Now we're just going to take things one step further. So they want us to find the derivative. Remember, the derivative of the function, so we call this f prime of x, is always equal to the limit as h approaches 0 of that simplified difference quotient. So 3x squared plus 3xh plus h squared. But typically these are pretty easy limits to evaluate. When you look at this limit, you're just taking 3x squared plus 3xh plus h squared, but all of those h's are going to 0. So the only term that survives that, and the only term that's left for your derivative, is 3x squared. And remember, when you see that derivative, that 3x squared, you want to think of that as a formula that will find the slope of this function at any particular x value. So next they ask us to find f prime of -1. In other words, find the slope of this function at this location. And all we have to do to find that slope is take the x value, plug it into the derivative. So that's 3 times -1 squared. That's positive 3 for the slope. Finally, f prime of 1.5. So I'm taking this x value, I'm plugging it into this derivative. That's going to tell us the slope of our function at that location. So that's 3 times 1.5 squared. And I'll do the calculation with you on that one. I don't know that off the top of my head, so I'm going to take 3 and then times 1.5 squared. Let me get that typed in correctly. So 1.5 squared. and I'm looking at 6.75 for the final slope. Okay, we're going to do one more example for the first part of this lecture. So this is going to be down at the bottom of page 3, and it's basically just going to put some of these ideas together. Remember the previous two examples, we found the derivative for x squared, we found the derivative for x cubed. What they ask us to do in this little quick check here is to use the results from examples 1 and 2 to find the derivative of this new function f of x, which is x cubed plus x squared. And then we'll calculate f prime of negative 2 and f prime of 4. Pardon me. So let's start with the derivative. If I want the derivative f prime of x of this new function, well, remember, we've already found the derivative for the individual terms. The derivative for x cubed was 3x squared. We got that from example 2. And then plus the derivative for x squared was 2x. We got that from example 1. So if the function is created just by adding those two together, the derivative is created in exactly the same way, just adding those two initial derivatives together. And remember, this derivative is basically a slope formula for this initial function. So if this is the original function, f of x equals x cubed plus x squared, we now have a formula for this function to find its slope at any particular x value. So let's start with f prime of negative 2. So I'm just finding the slope of our function at this particular x value. So that's going to work out and give us 3 times negative 2 squared plus 2 times negative 2 as well. So in this case, I've got a 3 times 4, that's 12. And then I'm going to subtract a 4 from that. That's positive 8 for the slope. That's the slope of the function at that location. Notice they ask us to interpret the results. So that's the interpretation. This is the slope of our function at that x value. Finally, they want f prime of 4. So that's going to be a 3 times 4 squared plus 2 times 4. So 3 times 16, that's 48. And then I have to add 8 onto that. So that's a 56 total for our final answer. And I think this is a good place for us to pause. So I'm going to cut off the part 1 video here, and then we'll pick up with a part 2 video where we continue this discussion and look at a couple of additional examples.